Good morning, everyone. Miss Buller here. Kind of felt like Mr. C was stealing the show for a little bit, so it's time for me to make my own video, and I'm going to talk to you about reaction mechanisms. This just gets me every time. It's so funny. I can't wait for you to understand what all of this means, and it'll be as hilarious for you. So the goal, by the end of this video, you can look at this little cartoon, this joke here, and understand exactly what it means. So funny. So I have a confession to make. In honors chem and regular chem, we've lied to you. We tell you that you start with these reactants and you make products. It's that simple. What you start with is what you get, but that's not the real truth. Not really hardly any chemical reaction. What you see when you see the balance equation is exactly what's going on. The truth is that there is something called a mechanism, and these are multiple small steps that we call elementary steps that make up the reaction. So it's never like, for example, you tell your parents, like they say, like, what'd you do today? And you're like, well, I went to school and then I drove home from school. That's not really the day. You go to first period, and then you go to second period, and then you go to third, and then you go out to lunch, and you pick up a friend, and you go through the drive-through, and then you come home, or then you go back to school. Maybe you have an off period, right? So like when you just say, yeah, I went to school and then I came home, that's the balanced equation, right, from start to finish. But the reality is there were a lot of steps in your day that you're leaving out. That's what the lie is that we've been telling you. We have been leaving out all of those little steps. So that balanced chemical equation is helpful, don't get me wrong, because it tells us the reactant, the products, the stoichiometry, but it doesn't give us about like how is it actually happening, who's colliding with who, how do we rearrange to make those products. All right, so let's talk about what this means. I see a table here that says elementary reactions, and really an elementary reaction is a small step of an overall reaction. So an overall balanced equation, elementary are these small steps that are actually occurring, right? Go to first period, talk to your friend, drive to lunch, things like that. And notice there's accompanying rate law. So let's look. If I just have reactant A going to the products, that's called unimolecular. That means we have one molecule that's doing the heavy lifting for this step. So a rate law for that one step would be rate equals K times the concentration of A. Well, what about these two? Bimolecular is going to be two molecules that are involved in this. Remember, these are elementary steps, small steps to the overall reaction. So maybe two of A collide in this step to rate equals K times A squared. Or maybe A collides with something different called B. The rate will be K times A times B. There are also termolecular, which means three molecules are involved. And I would like to just forewarn you, this is very rare. It is very hard, we saw in the collision video, for three molecules to collide at the exact same moment with the correct amount of energy with the correct orientation. So the termolecular is rare. So the molecularity of a process tells us how many molecules are involved in that particular step. And if you notice, something that might be new here is that the rate law exactly corresponds to the stoichiometry. Look at 1, 2, 3 A's in that step, A to the third. That's only going to be for elementary steps. So I'll talk about that a little more later. But remember, elementary means these are the smaller steps in the reaction that we might not see from the overall balanced equation. So here's where the lie is. If we see this reaction, we have ozone going to oxygen, and it says things are not always happening this way. It's not as simple as that two O3 molecules collide and rearrange to make 3 O2. It actually happens in this two-step mechanism. So first, this is going to happen. Step 1. I'm going to have one ozone molecule break down into an O2 and a single oxygen. And then step 2 is going to happen where we have a second ozone molecule reacting with that same O from above to make two O2 molecules. So this is a two-step process. So this says, part A, describe the molecularity of each step. Well, let's look at step 1. Step 1, we just have one thing that's breaking down. Molecular, there we go. In step 2, I have this molecule colliding with this molecule, making it bimolecular. So that's the molecularity of each elementary step. Now let's write the balanced equation. So they gave it to us up here, but we should be able to get the same reaction. It's kind of like a math problem. So here we have our arrows. Make sure it's really actually nicer when those line up, but we're going to add up the steps. The trick is anything on the product side, and that's also on a reactant side, is going to cancel. Here's what I mean. So I see O3 on the left of the arrow and O3 on the left. I see O2 on the right of the arrow, 2 O2s on the right, and then I see this guy, let's go with, I need a new color. I see this guy on the left of the arrow and same thing on the right. So that's going to cancel out. It's kind of like when you have something on your reactant side, something on your product side, like almost like a spectator ion would act. We're going to cross it off. It's not a spectator ion, but it's similar. Okay, so we're going to just add up anything that we haven't crossed off because it was on both the right side, the product side, and the reactant side. So I see that there's 2 O3s. And then everything else on the reactant side has been crossed off, making 1 here, 1, 2 there, so 3 O2. Does that match? Absolutely. So notice when I added up those 2 steps and crossed off the thing that was on the product side and the reactant side, we got the same balanced equation. The next thing says to identify the intermediates. Let's flip over a slide real quick. So the definition of an intermediate is something that is created in one step of the mechanism and used up in a later step. Okay, they don't have to be back-to-back steps, but in this case they are. So oxygen, single oxygen here, was made in step 1 as a product, and then I used it immediately after as a reactant. That's why we crossed it off. It wasn't in our balanced equation, but it makes it an intermediate. So it will never see an intermediate in the balanced equation, but it's something we actually made in the reaction and then used it up very quickly in the next step. So if I give you reaction mechanism, so the multiple steps, maybe there's 2 of them, maybe there's 3 steps for this full reaction, you can actually figure out the rate law for the overall equation by using something called the rate determining step. The rate determining step, the one that determines how fast a reaction can happen, is the slow step of the reaction. So you may have, if you're an athlete, maybe you've heard the reaction, you're only as fast as your slowest runner, you're only as strong as your weakest teammate, things like that. Same thing with mechanisms. So if I have 3 steps, but my middle step is the slow step, that's going to determine how fast I can go. I'm kind of hungry, even though it's 6 in the morning, but I think of Chipotle. You go to Chipotle, and you got the first kid who heats up your tortilla. Then he passes on to the kid who does the rice, the beans, the meat. Then they pass it on to the toppings person that maybe does the guac, the cheese, always guac, by the way. It's always yes. Why would you? Yeah, it's extra. I don't care. That's why I'm here. Anyways, all those toppings, right? Then there's sometimes if it's really busy, a certain kid wraps it up, and then you have the cashier, right? That's like 4 or 5 teenagers, and I'm trying to like get my burrito, right? But at Chipotle, I'm only gonna get my burrito in my hands, in my belly, as fast as the slowest kid in that line works. For example, if the cashier cannot make change quickly, it doesn't matter how fast they heat up my tortilla, I'm going to be slowed down by the cashier not able to count money for the people in front of me. Let's say Tortilla Man is very slow. He's chit-chatting, he's texting his girlfriend while I'm waiting, right? It's gonna take me slower to get my overall burrito because of that Tortilla Man. Or maybe Guac Girl is really, really slow in the middle. It doesn't matter how fast the cashier is working if Guac Girl scoops the guacamole slow as molasses, right? So your rate determining step is the slow step in the process. Whoever the slow step is will determine your rate law. So we have steps, and I want to warn you, your book does the steps differently. Don't panic if you want to try to learn that method too. Great. I can try to get the rust off and remember how I learned how to do it, but this step is way faster than what the book's showing you. So skim through what the book says, but if it confuses you, always you can revert back to these 4 steps. So if you know the slow step and you have a mechanism, multiple steps, draw a line under that slow step. You're going to box everything up into the left. So if I drew it here, I'd box everything up into the left of the reaction arrow. And you're going to write down everything up into the left of that line except for intermediates in the rate law. The stoichiometry of the coefficient is the order for that chemical. So before, we had to experimentally determine the coefficient. We used the differential rate law, or the method of initial rates as it's formally called, and we found where maybe one thing changed and one thing stayed the same. We figured out how it impacted the rate. But with mechanisms, you can just use whatever the balanced equation says as your exponent in the rate law. All right, so if that confused you, I'm a much better teacher when I can give you examples. So this would be a good free response question. Notice letter A says write the equation of the overall reaction. Sometimes FRQs try to help you with the order of the questions they ask. So even though I see that this is a two-step mechanism, two different steps, so step 1 is here and step 2 is here, and they've identified what's slow, what's fast. Even though I can kind of predict that I'm going to have to maybe write a rate law for this, I'm not going to do that because that's not what it asked me to do. It said write the equation. So we're going to look. N2O makes N2 and O. N2O again, but they're on the same side, makes O, or plus O, so there's an intermediate. I made it in step 1 and I used it up. Makes N2, so another product, and O2. So if I add these together, I see 2 N2O gas, and then we cross off the intermediate. I see 2 N2 gas, and I see 1 O2 gas. So that is my balanced equation. So this reaction that we're looking at right here doesn't actually work the way we see it. It actually goes through a two-step mechanism. Now letter B. If it's okay with you, can I erase? Well, that's silly. Okay, guess not. We'll use a different color. Yellow. Write the rate law. So remember, we're only as fast as our slowest step. So step 1 occurs very slow, and then the second step is fast. That's great, but that's like having a race and you have the turtle start off the track race, and then you have the rabbit running at the end. Well, the turtle is going to be so slow that by the time the rabbit even gets the baton, it doesn't matter. So here's what we do. We draw a line under the slow step. We box everything up into the left of the reaction arrow, and then we write our rate law. Rate equals little k times N2O, and in this part right here, there is only one of the N2O, so it's to the first, okay? We are only allowed to use the stoichiometry as the order, so the fact that there's a 1 here and put it here, we're only allowed to do that when it's coming from the elementary step of a mechanism. Okay, mechanisms are just proposed. I'm going to talk about that later. This is not known to be fact. We can be pretty certain that it happens this way, but it's proposed. If I want to know for certain the rate law of this overall reaction, if I want to know for certain that this is the correct rate law, I would have to do an experiment. But based off the way this mechanism is written, this proposed mechanism, here is the rate law for this overall reaction. Okay, so the reaction A plus B plus C makes ABC actually occurs in 2 steps. We're going to do A plus B makes this transition, or this intermediate AB, and that intermediate AB reacts with C to make ABC. 2 steps, slow and then fast. I can draw an energy profile like we saw in the video with Mr. C, like this. A and B, we go up to a transition complex. We fall down. Here's my intermediate AB. We made that intermediate up here. Okay, made the intermediate AB, it reacts with this new reactant C. In a fast step, there's a new transition complex, and then we make ABC. So you can see a 2-step mechanism, 2 transition complex. And remember, the transition complex is when A and B react, they have to reach this activation energy. So it's kind of like A and B are at the point where they're almost this new thing, AB. To me, it's like when you go in a changing room. Dudes, maybe you don't know this feeling, but you put on a dress, ladies, and you're like, right? And you have a moment where that dress could go back on the rack, you don't buy it, or absolutely you're going to walk out of the store and buy that dress, right? So that's the same thing that's happening up here. Do we have enough energy? Do we like it enough? If we do, then we fall down. Same thing here, new transition state. Yep, we like it, great. Notice the slow step on this energy profile has a very large activation energy. So that bigger activation energy, that steeper hill, that means it's the slow step versus the second step has a lower activation energy. Okay, overall the reaction, here's A and B. Here's my products A, B, C, right? We could draw probably an overall curve of sum, but the reality is we're trying to show it in two separate steps. So there's two different transition complexes for the mechanism. So with mechanisms, there's some rules. I told you earlier, mechanisms are just proposed. So we are proposing, hey, I think this reaction I'm looking at happens in these multiple steps. Well, how do you know if you're on track? Like, I'm just in AP Chem, how am I supposed to propose a mechanism? Well, there's two things, and both of them have to be true for a mechanism to be accepted. First, the sum of all of the elementary steps have to add up to the overall balanced equation. We cross off the intermediates, they have to add up to the overall balanced equation. That's easy. And then the mechanism must agree with the experimentally determined rate law. So we just figured out the rate law in the last problem by using the elementary steps, by drawing the line under the slow step and boxing everything. Well, I could also do experiments like we've been doing and find the rate law that way, and they have to agree. If one of these is not true, then it is not an accepted rate law, not an accepted mechanism. Both of these things have to be true, and then the proposed mechanism is accepted. So it is possible, actually, that there are multiple possible mechanisms for one reaction, because as far as we know, if they add up to the balanced equation and it matches the rate law, then it could be acceptable. So if I'm a chemist, how do I actually figure out a mechanism to propose? Well, first I need to determine the rate law through experiments. So either find the integrated rate law, find the differential rate law by doing multiple steps. That's the method of initial rates. So you change the concentration of one thing, leave one constant, measure the initial rate that way. Then, once we know the rate law, the chemist can construct possible mechanisms and experiments and eliminate least likely possibilities. So, for example, we know three things are not likely to collide. Like, that's less likely than maybe if you have a mechanism where most of the steps are one or like unimolecular or bimolecular. Okay, and then the mechanism can never be proved absolutely. So that's why we say it's a proposed mechanism, because again, we can't actually break a reaction down. These steps happen really fast, step 1, step 2, so we can't actually slow it down and zoom in far enough to really see what's going on. All right, here's a good FRQ question, and I want you to pay attention to the level of detail in my answers. Some of us were long-winded in our first test, so this would be a great FRQ. Let's see how short and sweet I can make it. So what is the overall reaction? Well, let's first look and see if there's anything I can cancel. I see I make some chlorine here and then use it up, and everything else looks good. So let's add it all up. I see 2 NO2Cl. When those are all added together. I see 2 NO2 gas, and I see 1 Cl2 gas. Okay, is Cl a catalyst or an intermediate? Well, I haven't taught you about catalysts in these reactions yet, but I see I made it in step 1 and used it up in step 2. So I'm going to say that Cl gas is an intermediate. It doesn't say to explain, but I'm just going to add a quick bullet point that it's made in step 1 and used up in step 2. Again, I probably could get away with just saying Cl is the intermediate, but that didn't take me very long to write. So it's a quick showing the grader that I know what an intermediate is and I didn't just randomly guess. C, what is the rate law for each of the elementary steps? So first I'm going to write one for the slow step. So they want a rate law for each step, not for the overall balanced equation, and then the fast step. So for the slow step, I'm going to use this guy, rate equals K times NO2Cl, and there's one of those. And then just the fast step, I'm going to use this guy, rate equals K times NO2Cl. There's one of those, and there's 1 Cl. So, couple of comments. In your book, one of the ways to find the overall rate law, in our step, we draw a line under the slow step, box everything up and to the left, right? But one way your book goes through is actually writing the rate law for each step, and then you end up canceling things out, like the intermediate would cancel out, things like that. So that's how they explain it in the book, which is where this question is coming from, because a lot of students will actually solve by using the rate law from both steps individually. That's not the way we're going to solve in this class, because my way is actually faster. So if this confused you, don't stress about it. It's really just it was meant to be a setup question to help kids with letter D, but the method we use to solve for the rate law in our class is easier. If you want to see where this comes from and why it would be helpful, read your textbook section on this and look at the example problems. Okay, anyway, so I want to know the rate law for the overall reaction. So I want the rate law for that equation. Well, we know the rate determining step is the slow step. So I draw a line under, oops, good try. Can I have maybe a little bigger? So we're going to draw a line under the slow step. Let's try that one more time. We're going to box everything up and to the left. So the rate law for this reaction here, the overall reaction based off the slow step, is K times NO2Cl, and there's just one of those, so it's to the first. All right, I want you to pause the video and try this question. So pause it, try A, B, and C, and then I'll put up the answer and have you check. So I'm pausing, you're pausing, and the answers come in 3, 2, 1. Okay, so I know I've really marked this up, but let's talk through. So it wants to know first, is NO2Cl2 or NoCl2 a catalyst or an intermediate? So I see I made it here and used it up. So it's an intermediate made in step 1, used in step 2. And this one, they gave me the balanced equation and they gave me the rate law up here. So we are in charge of figuring out the slow or the fast step. Well, let's first look, what if the second step was the slow step? Let's see, let me get my highlighter. So if this step was the slow step, I would box everything up and to the left, and everything would be in my rate law except intermediates. So that means there's NO here and NO here, so that's NO squared, and then there's one Cl2, one chlorine gas, so that would be chlorine to the first. So I'll do it like this. This guy would be this guy, right? And we don't put intermediates in our rate law. So if step 2 were the slow step, this would be the rate law, which doesn't match the rate law from the experiment. So let's see, what if step 1, which is my blue line, what if step 1, I'll use green right now, what if step 1 were my slow step? Well, here, we box everything up and to the left, so my rate law would be 1 of the NO, and 1 of the chlorine. So that tells me, based off these two options, the slow step must be the first step. So in this question, which step occurs the fastest? The second step is the fast step. Okay, which step determines the overall rate? Well, the slow step determines the overall rate. This is step 1, and that matches the experimentally determined rate law. All right, one more for you to try. Before you start, remember a catalyst is something that speeds up a chemical reaction, but it's not consumed. So we know that like an intermediate is something like this. IO minus, we used it up, or we made it, in step 1, and then we used it up. A catalyst would be something like I minus, where I start with it and then I end with it. Right? So I started with I minus, but I didn't actually use it up to make something new. I ended with the exact same thing. Okay, so I'm gonna pause, or you're gonna pause the video and we'll come up with the answer in 3, 2, 1. All right, so just so you're aware, this problem did have that catalyst. It's something that we will write in the rate law because it does impact the rate of the reaction, but it won't be written in the balanced equation. So, A is what is the overall reaction, so I canceled out the intermediates and I canceled out the catalyst, right? Intermediate on the product side, reactant side, catalyst on the reactant and the product. So if you look, here's my reaction when I add everything up. I do sometimes what's common, since we're not going to write the catalyst on either side, we put it above the arrow sometimes to indicate that it's a catalyzed reaction. So they want to know, is I minus a catalyst or an intermediate? We kind of talked about that. Here's my reasoning. It starts in the first step and is a product in the last step, so it's not used up. Is IO minus a catalyst or intermediate? It is an intermediate because we made it in step 1 and used it in step 2. Here's where it says to write the rate law for the slow and the fast step. So I did those, drew a line under each. But again, this is only helpful if you solve these problems the way the book does. And then the overall rate law. So they told me the slow step. So I draw a line, I box everything up and to the left. We don't put intermediates in the rate law, but we will put this catalyst. So my rate law is H2O2 to the first, I minus to the first. So this is the rate law for the overall balanced equation that we got in part A. So the catalyst does need to be in the rate law because the initial concentration of that catalyst will impact the rate of the reaction, unless it's something called pseudo first order, which we saw in our lab, where basically we make this so big that it's not even really changing. And so that, because we're holding it constant, it's not really impacting the rate, but we can talk about that more in our lab. So every step in a mechanism has its own little K value, its own rate constant. We'll talk about these arrows in a second, but basically if this is step 1, it has its own K, step 2 has its own K, which is why essentially we can write rate laws for each step if we want. Identify the intermediate. Hopefully you see that the intermediate is this equation, or this chemical ES. The catalyst is one that we start with and then end with, so that would be E. Okay, we're going to learn about equilibrium next unit, but these double arrows mean equilibrium. So it means the forward reaction is happening and the reverse reaction. If one of the steps is in equilibrium, when we draw our line and box everything up into the left, we include the products. So normally I would draw my line and box everything up into the left, but I really need, when it's at equilibrium, to draw my line, box everything up into the left and the product side of just the reaction that's in equilibrium, because that means we're also going in this direction, so it's part of the rate law. The nice part about this one, and what happens a lot, is that usually we have an intermediate that gets crossed off anyways. So on this case, my rate, because this is an intermediate, we don't include it, would be K times NO squared, because of that 2, times O2 to the first. But had this not been an intermediate, we would have included it in our rate law. All right, so here's our joke. I'm so excited for you to understand. So we're gonna have a unit on thermodynamics up here, and essentially it's like your reactants, your products, you're hungry, did you get fed? So it's like, did it happen? Did you consume food to be fed? That's it. Yes or no, does it happen, does it not happen? The middle one is what we've been studying this unit. So this is an uncatalyzed reaction where we're gonna do some cooking. So how much energy does it take to cook? That's our up here. How much energy is it gonna actually take to get me to cook this food? How long will it take? How steep is this, right? And then I'm happy camper when I'm fed. Now that we know about mechanisms, there's lots of different steps, and this is also a catalyzed reaction. So multi-step, I have to decide what restaurant we're going to. Then I have to decide what to order. Then I have to pay who's getting delivered, right? And so the reason this is catalyzed is because that takes a lot less activation energy, even though it's multiple steps to do these things, right? Overall, this is shorter than this whole thing, but I start hungry, I end fed, and this one's a multi-step because of all of those little details that are involved. So a 3-step mechanism for this catalyzed, meaning lower activation energy reaction. Isn't that such a good joke?